Hello and welcome to another Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 3, Lesson 8 on average rate of change and motion. So in the last lesson we looked at average rate of change, and if you haven't looked at that lesson yet, I would highly suggest that you do so, right? Because average rate of change was all about how fast a function's values were changing compared to how fast the input value was changing. And all the answers, at least in applied problems, always had per units on them. So rate units like cups of lemonade per hour or people per minute, something like that. But there's a special, example of average rate of change, and that's how fast things are moving. So today what we're going to be doing is we're going to be looking at average rate of change and motion, and specifically talking a little bit about the idea of speed. All right, so let's kind of jump into that. Average speed. The average rate of change tells us how fast the output of a function is changing compared to its input. Average speed is a special type of average rate of change, and specifically the average speed, remember these little triangles stand for change in, we call them the delta letter from the Greek alphabet, delta D over delta T, the change in the distance that an object has traveled divided by the change in the time that it's traveled, all right? Now again, speed is something that you've been kind of exposed to since the first time you ever got in a car, right? You look down or you look at a speed sign and you say, the car is going 62 miles per hour. Or that person is running at a rate of 22 feet, per second. That would be very fast, but whatever, the idea. So let's talk about average speed. Exercise number 1. Mia is going for a run and has an app tracking the distance she has traveled as a function of the length of time she has been running. The data is shown below for selected times. Letter A. What is Mia's average speed for the entire run? Include proper units in your answer and round to the nearest hundredth. I guess now would be a good time to mention that a lot of the calculations we do today are going to be rather messy. They're going to have a lot of decimals involved and things like that. So you don't want to have to spend a lot of time doing long division by hand or anything like that. You can definitely get away with just using a calculator that's either on your phone today or a scientific calculator. I'm going to be, as always, using the TI Inspire CX calculator that I've got kind of hidden down at the bottom of my screen. So let's talk about it. What is Mia's average speed for the entire run? Well, that's easy enough because you kind of look at how far she went. And over her entire run, right, she ran 8.8 miles. How long did it take her? 75 minutes. And generally speaking, you've been learning about speed probably for a while. Generally speaking, people think of speed as distance divided by time. And that's not a bad way to look at it, especially in letter A, right? Because then I can just say, well, I've got 8.8 miles that have occurred over the span of 75 minutes, right? And therefore, what do I get? 8.8 divided by 75. All right, I'm going to round that to the nearest hundredth. 0.12, right? Yeah, 0.12. Specifically, miles per minute, right? So for every minute that goes by, Mia has run 0.12 miles, or if you like it better, miles/minute, right? 0.12 miles per minute. That was her average speed over the entire trip. And again, we talk about average speed because at some points Mia is going faster and at some points Mia is going slower. But on average, she is covering 0.12 miles for every minute that she's running. Now let's take a look at letter B. Is Mia running faster from 10 to 25 minutes or from 40 to 60 minutes? Support your answer with proper calculations, as opposed to improper calculations. Okay, well now this is where it gets a little bit trickier, right? So let's hone in on that 10 to 25 minutes, right? So after 10 minutes, Mia has run a total of 0.9 miles, and after 25 minutes, Mia has run a total of 2.6 miles. So what we really need to do is we need to figure out how much distance she traveled during that time. So that's 2.6 miles minus the 0.9 miles, right? And that's going to be 1.7 miles that she traveled during that time. How long did she run? Well, that's a little bit easier to calculate, right? That's going to be 25 minutes minus 10 minutes, so 15 minutes. So the way that we kind of want to think about this, right, is exactly how we thought about letter A. The big difference is in letter A, we could just say, hey, she ran 8.8 miles in 75 minutes. Right here, we actually have to figure out how far she went from 10 to 25 minutes by subtracting this distance from this one, and then how long it took her by subtracting this from this. And then once we have 1.7 miles divided by 15 minutes, we can then do that division on the calculator. 1.7 miles divided by 15 minutes. That gives me very close to what I had before, 0.11 miles per minute. Okay, and leave me with a lot of room to do the other calculation, but somehow we'll squeeze it in there. What I'd like you to do now is pause the video and see how fast Mia was moving from 40 to 60 minutes, and then compare the two and figure out during which interval was her speed greater, which interval was she running faster. Pause the video now. I'm going to see if I can somehow loop all of this and move it over to give that didn't work. One more time. Oh, yes. Give myself a little bit more space on the board. All right, so from 40 to 60 minutes. All right, that's kind of the next time interval up. So 40 to 60 minutes, again, I'm going to do that 7.3 miles minus 4.5 miles, right? And that is 7.3 minus 4.5, 2.8 miles that she ran, divided by how much time she was going, 60 minutes minus 40 minutes. So she was running for 20 minutes during that interval. So now I'm going to just divide that by 20. And I'm going to get 0.14 miles per minute. So, like all speeds, right, you know, she's running 0.11 miles per minute here, 0.14 miles per minute there, so she's running faster from 40 to 60 minutes. Right? That's simply a greater speed. Faster from 40 to 60. And again, it's just sort of like saying, look, I just got to figure out how far she went and how long she was running. But in order to do both of those two things, I have to subtract the two distances, I have to subtract the two times, and then I have to divide. That's it. All right, let's take a look at one more. Well, actually, I guess a couple more. Let's take a look at letter C. Mia warms up for the first 10 minutes of her run and cools down for the last 5 minutes. On which of these intervals is she moving faster? All right, so I would like you to figure out over which interval, the first 10 minutes or the last 5 minutes, was Mia moving faster. Pause the video now and see what you can find. Well, the first 10 minutes, that one's easy because she's starting at 0, 0. So for the first 10 minutes, we can simply say, look, she ran 0.9 miles divided by 10 minutes. So for the first 10, right, it's very simple, right? Her speed will be 0.9 miles divided by 10 minutes, which is easy enough to do in my head, 0.09 miles per minute. Now, for the last 5, that's also pretty easy because I think I can do the subtraction in my head, right? She's got 8.8 miles here and 8.4 miles there. So that's going to be 0.4 miles that she traveled during those last 5 minutes. And of course, that's just divided by 5 minutes. That one's a little bit harder. So I'm going to do 0.4 divided by 5. And I'm going to get 0.08 miles per minute, which tells me that she is just barely running faster during her warm-up than her cool down. That maybe makes sense, maybe it doesn't, but you know, slightly faster. Okay. Now let's look at the last two problems. Letter D. Is there evidence in the table that Mia stopped during her run? Explain. All right. Well, I don't know. What I'd like you to do, take a look at the table, look through all the distances and whatnot. Is there any evidence in this table that Mia stopped during her run? All right. Now, notice how I asked this question. I asked, is there evidence in the table that Mia stopped during her run? I did not ask, did Mia stop during her run? Okay? I don't know the answer to that question. The answer very well could be yes. She could be running along, suddenly realized that one of her shoelaces was untied, stopped, tied it, took 15 seconds to do that, and then started to run again. And we didn't see that at any point in here because she didn't stop long enough. But the plain fact is, when I look at these distances, 0, 0.9, 2.6, 4.5, 7.3, 8.4, and 8.8, because all of those distances are getting larger, there is no evidence in the table that she came to a stop. If two of these distances in a row had been the same, then that would have been very clear evidence that Mia had stopped during that interval of time because her distance was not getting any larger. But the answer here is no, the distances are always increasing. Distances are always increasing. All right, and a final one, let's take a look at letter E. Mia is training for a marathon whose total distance is 26 miles. At the average speed that you found in A, would Mia finish the marathon in less than 4 hours? All right, so let's just be clear. Let's get that number down from letter A, right? In letter A, we found that Mia could run 0.12 miles per minute, okay? So let's, on average, write her speed. Average speed was equal to 0.12 miles per, not per hour, per minute. She would be going very slow if she was running 0.12 miles per hour. Okay, so what I'd like you to do now is play around a little bit. You're definitely going to have to use your calculator and see if you can figure out if at this average speed, Mia would be able to finish running a 26-mile marathon in less than 4 hours. Play around with it a little bit. Well, the key here is understanding that if I want to know how long it takes me to go a particular distance at a particular speed, I'm going to divide the distance by that speed, right? And this makes a lot of sense when you're thinking about, let's say, driving in a car, right? If I was driving 200 miles at a rate of 50 miles per hour, then it probably makes all the sense in the world that you'd do, well, 200 divided by 50, it would take me 4 hours, right? This is a little bit trickier because of how messy the speed is, but it truly is the same, right? If I take 26 miles and I divide it by 0.12 miles per minute, I'm going to figure out how many minutes it's going to take me to run this marathon. So let's do that. 26 divided by 0.12. All right, and that's equal to 216.6 minutes. Or I could round it, whatever. I could even say 217 minutes, right? So that's how long it's going to take Mia to run this race in terms of minutes. The question now is that greater than or less than 4 hours? And that's as simple as doing the following, right? I can now basically just say, all right, let me figure out how many minutes are in 4 hours, right? 4 hours times 60 minutes per hour is going to be 240 minutes. So it's going to take Mia 216 or 217 minutes if you'd like. So that's less, yes, less than 4 hours. It's important to be able to deal, especially in terms of time units, between hours, minutes, seconds, and things like that. Okay, let's keep going. Let's take a look at a little bit more. Motion is very often depicted in graphs. You see this all the time where you're given a motion graph and you have to think and interpret different things about the motion of the object. We can think about the average speed as being the slope of the graph over a particular time interval, right? And we talked a little bit in the last lesson about how the calculation of average rate of change really is just the calculation, or the same calculation as the calculation of the slope of a line. So, you can really kind of look at a graph like this and be like, oh, all right, the steeper the line, the faster or the greater the speed. So let's take a look at exercise number 2. A motion detector is placed on Hazel the Basset Hound. Basset hounds are renownedly slow on occasion, unless there's a sandwich involved. A motion detector is placed on Hazel the Basset Hound while she moves across a 100-yard football field. Her progress is shown in the graph below. Letter A, on average, what is Hazel's speed for the entire trip? All right, great. This is very similar to where we started the last time with Mia's run, except in that case, Mia's distance versus time, as a function of time, was given in a table. Here, Hazel the Basset Hound's distance versus time is given in a graph. So take a moment and figure out what Hazel's average speed is for her entire trip across this 100-yard football field. All right, well, that should be very easy, right? She has gone a total distance of 100 yards in 40 seconds. So her average speed, wow, her average speed is going to be 100 yards divided by 40 seconds, which is going to be 100 divided by 40, whoops, of course, which is going to be 2.5 yards per second. That might seem fast. Trust me, it isn't particularly. All right, so 2.5 yards per second is Hazel's average speed. Let's take a look at letter B. Is there any interval of time during which Hazel stops moving? How can you tell? All right, well, take a look and think about this and see if you can figure out if there are any intervals of time where Hazel has stopped moving. Well, one of the keys is if you're looking at a distance versus time graph, a distance graph on the y-axis, time on the x-axis, then anywhere you have a horizontal line, what happens is there's no movement going on. So specifically, Hazel is not moving during this section from, what is that, from 8 seconds to 20 seconds. And you can tell that she stopped moving because her distance is not changing, right? If the distance isn't changing, well, then you're not moving, right? In other words, she starts at 8 seconds at 32 yards. And after 20 seconds, she's still at 32 yards, right? And it's also clear that she hasn't gone backwards. If she had, then what we would have seen is we would have seen the graph go down and then back up. But the fact that it's staying all constant in here, right, that tells us that her distance is 32, yards from the start all through here, which means she's not moving. Okay, let's take a look at letter C. Is Hazel moving faster in the first 8 seconds or in the time between 20 and 28 seconds? Justify. All right, so again, why don't you go ahead and work that out, work out her speed for the first 8 seconds, and also work out her speed between 20 and 28 seconds, and then let's talk about over which time interval she's going faster. All right, well, for the first 8 seconds, the speed calculation is very easy because I can tell after 8 seconds, Hazel has gone 32 yards. So for the first 8 seconds, right, first 8 seconds, I can say that her average speed is 30, oh, wow, a little lag on the pen there. Is 32 yards divided by 8 seconds, and that's going to be 4 yards per second, right? So that's for the first 8 seconds. Now, for 20 to 28 seconds, I've got a little bit more work, right? Because Hazel starts at 32 yards, and then she goes to 70 yards. So from 20 to 28 seconds, right? The first thing I need to do is just figure out how much distance she traveled, right? She went 70 yards minus 32 yards, which is going to be, 38 yards, all right? All divided by 28 seconds minus 20 seconds. She does 38 yards in 8 seconds, okay, which pretty much tells you she went faster during that interval because she went farther over the same amount of time, but let's just get her speed, 38 yards divided by 8 seconds. And during that time interval, she was going at 4.75 yards per second. So she was going faster from 20 to 28 seconds. Not again by a lot, right? She was running 4 yards per second for those first 8 seconds. Then she was running 4.75 yards per second. And really, it's very kind of hard to tell this from the graph, but it's all about how steep that line segment is versus how steep that line segment is. And that line segment is just slightly steeper than that one. Again, kind of hard to tell, and I'm sure my hand is not doing much good there in trying to convince you, but it's all kind of about steepness. And again, just a little bit faster during that interval of time. Okay. Now, let's take a look at one last thing that can be tricky for people. It's important to pay attention when we are given a graph of motion to make sure we know what it's telling us. So let's take a look at exercise number 3. A company is testing the acceleration and braking power of a new car they have developed. They recorded the car's speed versus time in a trial with the results shown below. So before we even read letter A, let's just make sure we understand something. In the last problem, the y-axis was the distance Hazel had traveled, and the x-axis was the time she had traveled. In this particular problem, the y-axis is the speed itself of the car, and the x-axis is the time. So this is a very different graph. It's telling us something very different than the last graph did. It literally is telling me how fast the car is going versus how long the car has been driving. Now let's take a look at letter A. Even though this graph is horizontal, the car is moving from 10 to 15 seconds. How can you tell? So in other words, let's be clear, from 10 to 15 seconds, which is this interval in here, right? That graph is horizontal. And you know, I said in the last problem, if the graph's horizontal, there's no motion going on. But I claim actually in this graph that the car is moving over that interval. How can you tell? Pause the video now and think a little bit about exactly what the outputs of this function are telling you. All right, well, it's pretty much simple, right? The outputs of this function are not the distance that the car is. They're actually the car's speed. So after 10 seconds, the car is going 60 miles per hour. And after 15 seconds, the car is still going 60 miles per hour, right? So during that time period, the car's speed is 60 miles per hour. And if you think that, if you think that a vehicle isn't moving when it's going 60 miles per hour, I would suggest getting in a car going 60 miles per hour, right? And again, it's important. This graph is actually giving us, as its outputs, the speed the car is traveling at. So now let's take a look at letter B. Is there an interval of time when the car isn't moving? If so, when? All right, well, we already discussed it's not during this time interval. Maybe there's no interval where the car's not moving. Take a look at the graph again very carefully and see if you can figure out a time interval when the car, not the graph, but when the car is not moving. All right, well, there certainly is. And how do you know when something isn't moving? Well, it's when its speed is equal to 0. And that happens right in here, right? So from 20 to 30 seconds, and that's very simple because the car's speed is equal to 0. All right, right? When the speed's equal to 0, you're not moving. Now, finally, I love this one, letter C. What is the average rate of change of the speed from 30 to 45 seconds? Using proper units, explain the physical significance of your answer. All right. Well, first, I'd like you to try to calculate the average rate of change of the speed from 30 to 45 seconds, okay? Try to figure out what the units are of your answer. Those are a little tricky all by itself. And then see if using those units, you might be able to figure out what that average rate of change is telling you. All right, well, let's do it, right? So the average rate of change from 30 to 45 seconds will be the output here minus the output here. And really keep in mind, these are really coordinate points, 30, 0 and 45, 84. So it's really 84 minus 0, all divided by 45 minus 35. And that's going to be 84 divided by 10. And that's not 45 minus 35, that's 45 minus 30. So let's try to do 84 divided by 15. And bring up my TI Inspire. 84, what's going on here? Menu, escape. 80, it's just not giving it to me. There we go. 84, why doesn't my calculator work? 84 divided by 15 is, of course, oh, come on. There we go, 5.6. Whew, man, these calculators these days. 5.6. So that's the average rate of change. Okay, but I've kind of purposely left the units off so far. How do I think about the units, right? Well, I think about them as the units of the numerator divided by the units of the denominator. Well, what are the units of that numerator, right? That's 84 miles per hour minus 0 miles per hour. So the units of the numerator are miles per hour. I'll kind of give it that common abbreviation, MPH, miles per hour. The denominator is 45 seconds minus 30 seconds, or 15 seconds. So the units of this are miles per hour per second, right? 5.6 miles per hour per second. Isn't that cool? It's a rate within a rate, 5.6 miles per hour per second. And what it's telling you, right, is that for every second, the car's speed is increasing by 5.6 miles per hour, right? And that in physics is known as acceleration, right? Speed is how fast your distance is changing over time. Acceleration is how fast your speed is changing over time, right? And you see this all the time in car commercials when they'll say something like, well, that car can go from 0 to 60 in 5 seconds, right? 0 to 60 miles per hour in 5 seconds. By the way, if it did that, its acceleration would be 12 miles per hour per second. All right. Anyway, a little bit of physics there. Let's wrap this up. So today we looked at a very concrete example of average rate of change. Mostly we concentrated on the change in distance divided by the change in time gave us the average speed, or on average how fast an object was moving. In that final exercise, we looked a little bit at the change in the speed divided by the change in time, which is the acceleration of an object, but that we're going to be way less concerned with because it's a little bit more of a challenging topic. What you are expected to understand, though, is that connection between the speed that an object is moving at and, in general, the average rate of change concept. All right, well, we're going to certainly get a lot more work with average rate of change and a little bit more work with speed and motion as we move forward in this course. For now, I just want to thank you for joining me for another Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.